And now what you've been waiting for since last year when we had to take him off the stage with a hook is another historical perspective from the Where2O community's resident historian, Chris Spurgeon, this time taking us into space. Thank you very much, Chris, for coming back.
Thanks, man. Okay, I guess you can all hear me. Thanks once again, Brady. Thanks, everyone, for coming to Where 2.0. As Brady's mentioned, I've been here a couple of times before speaking about some of the clever things that have happened in mapping here on Earth. This time I'm going to gaze skyward and show you a little bit about how we map space, how we find our way through the heavens, how we navigate. So to begin, as I started researching this, I discovered a few facts came out over and over again, overriding kind of rules. The first rule is nothing in space stays still. It makes everything much harder than it is here on Earth. The Grand Canyon does move, but it moves really slowly. Venus goes a lot faster. What I'm trying to say is everything's a pain in the ass when you try to map stuff in space. Everything's tilted. So your frames of reference are constantly switching. Space is really big, so just even picking a unit of measurement causes all sorts of trouble. And because it's so big, so topsy-turvy, so constantly in moving, the only way we've been able to find our way around space, to be able to talk to each other about objects in space, is by picking common frames of reference. These techniques have shown up over and over and over again throughout history. So let's start by talking about probably the earliest way of location finding in space. Ever since there's been humans, we've been looking up at the night sky. And ever since we've been looking up at the night sky, we've found pictures in the night sky. We've found patterns. These patterns, of course, are called constellations. And constellations have been with us, we don't know how long ago. This is one of the cave paintings in France from 17,000 years ago. You'll notice those dots right there. That's a constellation. It was painted 17,000 years ago. So even back then, before written language, before any of our technological innovations, we were mapping the sky, looking at the sky. We were creating what became astrology. Now, astrology has given us two things. It's given us a lot of bad van art, but it's also given us these areas in the sky, the constellations. And these constellations are still used by not astronomers, well, they're used by astronomers too, to take your money, but they're also used by astronomers to define areas in space. There are now officially, and it is official by an organization called the International Astronomical Union, there are now 88 different constellations in the night sky. This arrangement of these 88 constellations and where their boundaries are were defined by this guy named Eugene Delport way back in 1922. And they are still, to this day, used as a shorthand navigator. So that's the first way that we find our way through the heavens. But just because we have that there, we still wanted and needed, and to this day need, more precise ways to locate spots in the sky. We can't, it's all well and good to say, oh, it's just over there in the constellation, Virgo. But we want to get things a bit more precisely. Here on Earth, of course, we have this very precise system of defining any spot on Earth using latitude and longitude. We have a similar system for space. And before I explain to you, I just want to say once again, with all these things, with all the mapping, with all the location finding in space, if you can simplify things down, it becomes much easier. In other words, the only way to do it is to lie. Of course, the Earth, we know, goes around the sun. It's also tilted and it's spinning, and the sun is going around the center of the galaxy, and the galaxy is going around the center of the universe, and so on and so on. We forget all of that with the main system that we use for finding objects in the sky. We lie to ourselves. We say, just like the Catholic Church liked, the Earth is in the center, is stationary, and the heavens are moving around us. The system that uses this is called the equatorial coordinate system. And it's in the same way that we have latitude and longitude for our terrestrial mapping systems, they use two terms called right ascension and declination. And I'll explain how these work. Declination is really easy. It's exactly the same as latitude. The Earth, wait a minute, hang on. Wait a minute, visual aid. Okay, the Earth, slightly smaller than actual size, spins like this, of course. And as it does, as it spins, it appears that the stars are moving around us. If you're on the equator, a star directly above the equator is going to be right above you. If you're at the North Pole, it's going to be on the horizon. The North Star, Polaris, is pretty much right over the North Pole. It's about 3/4 of a degree off. And so if you're standing at the North Pole, you see it right overhead. The angle, this angle, is exactly analogous to latitude here on Earth. They just happen to call it declination. And you can see from this drawing that you can see this drawing of the equator spinning this way, or the Earth spinning this way, and our equator cutting this big circle right through the heavens. In the same way that we do longitude on Earth, we do what's called right ascension. We decide how far around this way a given star is. And a couple little differences. We don't use, when you talk about right ascension, we don't use degrees. We use hours. And there's a couple reasons to do that. The big reason is, since the Earth, remember the Earth rotates, everything keeps moving in space. 1 hour of the Earth's rotation equals swinging 15 degrees, moving 1 hour in this right ascension coordinate system. So it's really easy to adjust your telescopes. What happens is objects stay in the same place in space as the Earth moves. So that's how we've marked up the skies for the heavens. There is one tricky thing, though. Just like here on Earth, the latitude is a natural phenomenon based on the Earth's rotation. So is declination in space. Just like on Earth, here on Earth, longitude is a completely man-made construct. We had to pick a spot on the Earth and say, this is our 0 point for east and west. We had to do the same thing in space. And where we picked the 0 meridian for right ascension in space is, I don't know, hope you can see it in the drawing here. I think you can see my cursor. It's right where the sun moving across the heavens slices the plane of the Earth's rotation. It's a point called the vernal equinox. It's in the constellation Aries. And we have decided by convention that's the 0 point when you look up in the heavens. Once every year, the sun moves all the way around and comes back to that 0 point again on or right about the first day of spring. So that's how we marked up the heavens. It's made astronomy so much easier than just saying, you know, it's in the constellation Drago, kind of near the tail, but a little bit off to the left. We can give it. We don't have to do that anymore. Since 1822, we've been able to give exact numbers and mean an exact point in the sky that everyone could understand. The next thing I want to talk about is how we mapped the first celestial body beyond our own Earth. And the first body we marked, or mapped, not surprisingly, is the moon. Now, of course, the moon has been this object of fascination, of beauty in music and literature and art for centuries and centuries and centuries. But starting around 1600 or so, when the telescope came into wide use, we also started doing a more scientific study of the moon. This map, for instance, was drawn by an astronomer in 1611, a guy named Thomas Harriot. And if you look at the screen, you'll see he's not too far from the real deal. As we got more powerful telescopes, we started mapping the moon with greater and greater accuracy. This caused a couple of things to happen. One, there was a huge rush of people wanting to name things on the moon. Every time you got a more powerful telescope, you could see more features. So people were naming things after their mistresses and after the people that funded their projects and after their after saints and after the town they were in and everything. It's madness. It's madness. To this day, this organization I mentioned before, the International Astronomical Union, is the official holder, the official keeper of names on the moon and the other celestial objects. So when they first wanted to start mapping the moon, they also needed a coordinate system for the moon. They thought, well, we're not going to use latitude and longitude because we always see the same side of the moon. One of the first proposals was to use this grid system. Basically lay a large grid over the full moon and just measure, just like we measure over pixels now. Just give coordinates like that. It seemed to make sense. However, when they started watching the moon more closely, they discovered a very big flaw. And if you look at the screen here, you'll see it. The moon, while we see the same side of the moon all the time, we don't see precisely the same side of the moon. The moon has a little wobble. Technically, this is called libration. We actually see, if you add it all together, about 59% of the moon. And this has to do with the eccentricity of the orbits of the Earth, the moon, and the sun, and the fact that the moon is not the center of mass of the moon is not exactly in the center of the sphere of the moon. So they realized, this whole graph thing is not going to work. So they realized they did actually need to impose a cartographic system on the moon, and they fell back on good old latitude and longitude. The moon does rotate, but it rotates at the same rate that it goes around the Earth, so we never notice, but it does spin on its axis. So we had an equator, but again, where do you come up with the prime meridian? Well, they picked a crater on the moon. There it is, you can see the arrow pointing at it. That's a little crater called Mostig A, and that is the prime meridian of the moon. It runs right through the middle of that, just like the prime meridian here on Earth runs right through an observatory in Greenwich, England. That was decided in the early 60s when we were first thinking about going to the moon. By the end of the decade, we had mapped the moon precisely enough and had gotten our navigational act together so well on the moon that we could do stuff like this. This is Apollo 12 on the moon. Oh, by the way, that's Apollo 12 in the previous shot, too. That's the lunar module of Apollo 12 going down to the surface. And it landed right there about 200 yards from the Surveyor 3 probe that had landed on the moon about a little less than 10 years before. My vote for the single best feat of navigation in human history. So anyway, so we now have a map of the moon with very precise latitude and longitude. We turned our eyes to Mars. We picked a crater there. It's that kind of big crater in the upper part. That's called crater Airy 0. And that's the prime meridian for Mars. Mars also rotates, so it has a natural equator as well. We picked a crater on Mercury. I don't know if you can see it. It's right there. It's a little tiny bugger named Hunkal. That's a Mayan word. It actually means 20. We didn't pick a prime meridian on Mercury. We picked the 20th meridian, and I'll be damned if I could find out why. But once you have a 20th meridian, you've got all the rest of them. When we got to the gas giants, we wanted to come up with a mapping system for them. You can't look down and see any physical feature on a place like Jupiter here because it's all covered in clouds. It turns out, though, once we got the first space probe to Jupiter, we discovered that Jupiter does have bumps and features. You can't see them visibly, but you can detect their magnetic fields. There are fluctuations in the magnetic field of Jupiter, and they picked one of those bumps, a magnetic bump, as the prime meridian of Jupiter. So as I was looking into all this, I discovered a really amazing thing. There's one person that came up with all of these. This guy. This is a guy named Merton Davies. Merton Davies has created the maps for more of the solar system than any other human being. He worked in the defense industry, worked at the Rand Corporation, and I tried to do a lot of research on him. It's all still classified. He died like 10 years ago. He did a lot of super geeky stuff with analyzing spy satellite photos, and then around the time of the Apollo program, they grabbed him to come up with systems for mapping the planets. And this guy, this little civil servant guy, got to map basically our entire solar system. Totally amazing. Okay, we're going to move on to the next thing I want to show you is how we came up with mapping where satellites are. As you know, there are thousands and thousands and thousands of satellites. These are the GPS satellites that are in orbit right now. If you want to see them in action, there you go. This is how many of you people are making your money right now by these satellites talking to us. But we needed, as we started launching satellites into space, starting in the 1950s, we needed a way to describe their location. It's easy enough to describe the sun or Venus, something that moves relatively slowly, but something that's whipping around the Earth every hour or every 90 minutes, much more difficult to describe. So a whole system was invented to describe, let me switch back here, to describe satellites. And it's all based on the work of this guy, Johannes Kepler. Johannes Kepler in 1605 invented or discovered the laws of planetary motion. Kepler, by the way, is my vote for the smartest human being that's ever lived. If any of you, think Newton or Einstein, I'm happy to, take you on in the bar after the conference. Kepler, I think, is the smartest guy ever. He figured out the planetary laws, and we use his laws to define how satellites move in space. It's based on 6 numbers, and I'm going to show them to you. We're going to need the Earth again. This is our satellite. So, number 1 is called orbital inclination. Satellites could be around the equator like this. They could be going around like this or in any orbit in between. This tilt is called the orbital inclination. That's the first number you have to know where a satellite is in space. There's a shot of, as of about 15 minutes ago, where the International Space Station and the Hubble Space Telescope are, and you can see the tilts. The International Space Station has a pretty severe tilt, about 50 degrees or so. The Hubble Space Telescope, a little bit less than that. Satellites are in many different tilts for lots of different economic and scientific and military reasons. Number 2 is eccentricity. Every orbit, Johannes Kepler told us, is an ellipse. But some ellipses are very round like this, some are very elongated like that. So you need to define that number, how far you're squished in. Semi-major axis. Basically, that's a long-winded way of saying, how big is this ellipse? Is it, just barely fits around? Is it bigger than this room compared to the Earth? It's the size of the orbit. You have to have that number. You have to have a number called the longitude of the ascending node. Terrible name. I didn't name any of these things. What that means is, say you're on an orbit like this and you're tilted. All orbits are tilted a little bit. How do you say where this orbit is tilted? Is it here? Is it here? Is it there? What they do by convention is they notice, let's say the satellite is going around this way, counterclockwise as you're looking at it from the North Pole. They notice where on the Earth or other planet it crosses the equator going back up to the northern hemisphere. They write down that longitude. That's called the longitude of the ascending node. So that defines how that ellipse is rotated in space. Even the worst term ever, the argument of para-apsis. All that is saying at its closest point, how close is this thing to the center of the planet? The orbit could be, pretty much, just above the atmosphere. If it's inside the planet, it means it's going to crash. If it could be quite a bit further out. It's just one more number you need to define, and we're only one number away from the whole thing. Mean anomaly means, okay, the one thing we haven't said, we've said all this stuff about the orbit, but we haven't said where on this orbit the damn satellite is. That number is where the satellite is on this ellipse at a known moment in time. When you take all those things together, you get a completely accurate, completely predictable definition of the orbit of a satellite or any celestial body. If you look at the Hubble Space Telescope's data, it looks like this. Those numbers define all these different values. This format, by the way, is called a TLE, which I thought would stand for something like super clever, something with terrestrial lunar insertion or something. It actually, TLE stands for two-line entry, because it's written on 2 lines. and you can, by the way, get a hold of these yourself. This is a, oh, I'm sorry, I'm going to say one more thing real quick. Again, huge pain in the ass. Now, we know how to define these orbits, but still, it's such a nightmare to figure out where it is on Earth. So what we do is we convert all of these numbers into things that we can use on Earth. Just tell us stuff like, where do I aim my satellite dish? It's going to come over the horizon over there and go over there. If you folks want to play with this stuff, I highly recommend you write down this URL right here, sdd.jpl.nasa.gov. This is an amazing free resource that it's an online calculator. It's what's called technically an ephemeris for celestial objects throughout the solar system. If you want to do stuff like figure out, if you're in Las Vegas tonight, when is Venus going to rise? I used this once to help a photographer figure out where the full moon would appear above Independence Hall in Philadelphia. If you're, if you find yourself sitting on Mars and you want to know which way to look to see Neptune, you can calculate it using the JPL ephemeris. It's an amazing piece of work. It has a web interface. It has a telnet interface. You can even send it email messages and get the numbers back. It's endless fun to play with. I say I'm out of time, but I would just like to say thanks very much. I'm happy to hang around and talk as much as any of you would like about how we find our way through space. It's endlessly fascinating. And meanwhile, to all you people that are making maps here on Earth, thanks very much. And